G'day and welcome to this our lesson today on rectangular hyperbolas. For those of you who are working with me in class, please feel free. In fact, that's not even a feel free. Please do that work. Fingers crossed, those questions will give you the best start at understanding rectangular hyperbolas. And for those of you who are watching in internet land, welcome, hello, and how are you? So here we go. Recap. Now, previously, we've been working on all the stuff regarding domains and ranges and functions and one-to-one functions and everything that we can to describe functions. Now, actually, we sort of did this backwards because now we're going to go back in time, or at least back in the textbook. And if you're wondering what textbook I'm talking about, it's the Cambridge Essentials series, which I'm currently teaching to. And we're going to look at some very, very important and specific graphs. One of them is a rectangular hyperbola. One of them is the truncus. One of them is the square root graph. And the other are circles. Circles are such an exciting topic. And we'll come to that in 3 lessons' time. But as it says here, today we're going to look at something called rectangular hyperbolas. Now, there are other forms of hyperbolas. And if you actually type in hyperbola into google.com, or .co.uk or whatever, you can actually see some pretty funky hyperbolas. But the ones we're dealing with are rectangular hyperbolas. And I suppose, importantly, let's actually look at what the equation of the function looks like. It's always good to start with a bit of an equation. Now, this here is what I call the base function. So whenever we do transformations, and yes, I hate to tell you this, we are going to come up with transformations and this awesome DRT thing. When we do transformations, we always need to know what the original graph looks like. And I call that the base function, okay? So the base function is the graph y equals 1 over x. Now, before I even start anything, I'm looking at this going, well, hold on a moment. If I have a graph that's going x along the bottom and y up the top, then I know there's a certain number that you cannot divide by and actually get a result. And hopefully all of you know that if I let x equal 0 in this, I'm going to get that y is 1 over 0, and then suddenly we're going to have all sorts of problems. Because if you put that into your calculator, you get undefined. Yes, you do. You get undefined. And that's not very helpful to anybody. So we have to be careful that obviously in some later part of this video, we're going to look at why x equals 0 cannot happen. But always really important in any exam to know what a hyperbola or a rectangular hyperbola might look like when it's been transformed. And as you can see here, there are 6 different functions. 1, 2, 3, 4, 5, and 6 different functions. And each one has an x on the bottom that has a power or a floating number or an index of 1. So it's a fairly big hint that that is going to be a transformed rectangular hyperbola. And if you start looking at it, well, this minus 1, that's a plus 3 on the bottom. This is a 3 on the top. We seem to have a plus 3 here. This seems to be getting far more complicated. I've got a 3 there and a 3 there and a 2 there and a 1 there. Well, as you're aware, we can actually string all of these transformations together. But before we rush forward, let us go to order of transformations. Now, I don't know whether you guys would even have a clue who this guy here is. This is obviously a doctor, and this is Mr. T. Mr. T was an awesome character in the 1980s when I used to sit there and watch the original version of the A-Team. Yes? Wow, and you had to knock him out. Oh no, you didn't. The other guy had to be knocked out. Anyway, too much information. So we are looking for, imagining this guy is called Dr. T. That is the order in which we have to do transformations. So Dr. T stands for dilations first, then reflections, and then translations. And it's really important that when you get an equation, for example, y equals 3, 2 brackets, x plus 1 minus 6, and let's put a minus sign there for a little bit of a giggle. When you look at this, it is so important that all of the work is about finding out what each of these numbers mean. So I know that this value here, this 3, is basically a dilation away from the y-axis. I've just learned to look and know what that is. This minus sign is actually a reflection in the x-axis. This -6 means we're going to move down 6 places. My whole function is going to be translated 6 units down. This 2 here Well, it can be all sorts of different things. Actually, it can be a dilation away from the y-axis, and it can also be a dilation away from the x-axis. We'll come back to that one a little bit later on. And that +1 basically means that there is going to be a translation this way. So, knowing that, if I know that I've got my base graph of 1 over x, then I can use this and stage by stage by stage, apply each of the different transformations and get to my final answer. All right, so with all of the rest of the work that we're going to do, you need to make sure that it's Dr. T. Here's the base graph. So we've talked about the formula. Now let's have a look at what it actually looks like, right? And I would absolutely state that you should memorize this. It is so, so important, right? For all graphs, you must be able to show x and y axes or intercepts on the x and y axes, any turning points, all asymptotes, and right on there the equation of the curve. So if I have a look here, this is my basic graph of y equals 1 over x. And what you'll notice is, all right, and it's really hard to see, I've actually drawn a dotted line along the x-axis. Now the reason I've got that there is because what I'm saying is that I cannot have a y value of 0. If I have the equation 1 over x, y equals 1 over x, if I put y as 0 in, then I get 0 equals 1 over x. Swap my x and my 0 over, and once again, I have a problem because I cannot divide by 0. So putting y equals 0 into this equation doesn't work. And also, there is, believe it or not, a dotted line there on the line x equals 0. And again, we've already said earlier, if I put x equals 0 into my equation, then I'm going to end up with undefined or infinity. Now, these two lines here, x equals 0 and y equals 0, are called asymptotes. Asymptotes. Now, for completeness, what it means is that your graph will get closer and closer and closer to both the x value, x-axis, and the y-axis, but it will never, ever cross. It will extend up to infinity, and it will extend to infinity that way, and possibly infinity and beyond, hello Buzz Lightyear, but it will never, ever cross that axis, right? Because we've already decided we cannot have 1 divided by 0. It is just not possible. Little bit of word of warning for exams, particularly if you are doing methods. You have to be very careful that when you draw these things, you do not have it touch or wobble. Now, as you can see here, in this section of my graph, I would have lost 1 whole mark. Why? Because in methods, they take down half a mark and then they round down. For every mistake you make on a graph, they knock off half a mark. Then they round you down. Okay? I think of methods as the only negatively marked exam going because it actually negatively knocks marks off and then knocks them down even further. So here, you'll notice my graph curves at the very, very top. You can't do that. You have that curve, you're in all sorts of trouble. What you'll notice here is that I've actually crossed the line. There, I've lost half a mark, which is rounded down. And here, I've got what we call my flick, my end of line flick. You remember when you draw a line and you just sort of go down and you flick up? If you have that little bit of a flick there as well, half a mark off, right? So graphs you have to be critically aware of to make sure not to make any of those silly mistakes. So we'll go back to my original graph. So in an exam, you will undoubtedly be asked to find important information, right? It will ask you to label things like asymptotes, helpful points, and it may talk about domains and ranges. It'll also ask you to work out axis intercepts. So in this graph here, I've now labeled my asymptotes. I would put on there my function, or my function, y equals 1 over x, and you put on some important points. Now, the great ones about hyperbolas is that 1, 1 and -1 are 2 really important points. Why do you need to put this on an exam? Well, generally speaking, because you're going to be asked to sketch these things, the examiners want to know that you've actually understood how to translate, how to dilate, and how to reflect. All right, they want to know how to do it. And the best way for them to do that, rather than you to just draw some random graph that sort of looks, they actually want you to put on a couple of points so that you can actually say, well, look, I know that the point 1, 1 transforms to become, I don't know, minus 7,6, for example, by following a certain set of rules, right? So it's critically important. And I can guarantee you, absolutely guarantee you, that they will ask you the domain and range. So if you remember, what is the domain? The domain is equal to possible x values. And if we look at this graph here, every single value is possible except 0, because we've said we cannot put 0 in. And the range, once again, every single value is possible. It looks like every single value of y can come out, except, once again, 0. So, as we say here, domain and range of my hyperbola. Really, really important. As I've said, asymptotes, just for your notes, if you want to print this off and stick it in, is a line such as the value of x or y increases or decreases, the graph gets closer and closer to the line, but never ever crosses it. Now, lots of people think that when you transform the graph, the asymptotes will stay exactly the same, and that was a really bad asymptote. It doesn't, right? If you were to move the graph 3 units that way, for example, then while your asymptote at y equals 0 would stay the same. Why? Because we've not moved the graph vertically. The asymptote that was at x equals 0 now becomes the asymptote at x equals -3. So I would draw my asymptote, I would sketch my graph, and then I would go on to work out my important points. More about that coming soon, okay? But just realize the asymptotes actually move as well when you transform this graph. So, knowing the base graph, we can now use it to transform, and who couldn't get excited about a transformer? All right, so we're going to deal with lots of examples, and we're going to look at reflections as they're the easiest, then dilations, and then translations. Now, I know that goes against my Dr. T, but as I'm doing them isolated, then that's fine. We can look at reflections first. So here we go, reflections of rectangular hyperbolas. If you actually reflect in the x and the y-axis, have a look what happens. Here is my original graph. Now, if we reflect that in the x-axis, all we're going to do is just flip it. And as you can see, yes, that's the graph we get. And looking at it once again, I would need to have labeled my function. I know I've got it down in the bottom here, but I need to put it beside my graph. So I'm going to do y equals 1 over x. I would need to label my asymptotes. So I have x equals 0 and I have y equals 0 on there somewhere. What else would I need to know? Are there any axis intercepts? No, there aren't. My domain and range haven't changed because I have just flipped them. But my coordinates have, right? So I need to now notice that my coordinates have now gone to 1, minus 1 and minus 1, 1. So that was the reflection in the y-axis. What happens when reflected in the x-axis? What happens when reflected in the y-axis? Well, funnily enough, it comes up with exactly the same thing. OMG. Mind blown. Yes? Now, if we go back to the algebra of all of this, and we remember that our base graph is y equals 1 over x, then following these shortcuts, if you remember, when we reflect in the, let's do the y-axis, you replace x with minus x. So everywhere we see in the function, we see an x, we replace it with minus x. And it just so happens that by convention, we tend to put the minus sign at the top. So there is my algebra for a reflection in the y-axis. When we have the x-axis, you replace y with minus y. And lo and behold, once again, that becomes minus 1 over x. So that actually explains, just using the algebra, why their reflection in the x and the y-axis looks exactly the same. So that's reflections, nice and easy. Let's look at these dilations. So we can dilate away from the x and the y-axis. So if we look at the dilation from the x-axis first, so I've said factor A, doesn't matter what factor you can have anything you like. In this situation, I've actually dilated away factor 2. How do I know that? Because I've now looked at my points there and I've gone, hold on a moment, my y value has actually become twice as much as it was. Now, you're going to say, what do you mean it's become twice as much as it was? Remember, the standard hyperbola, and that is a really bad diagram. In an exam, I'd get no marks. The standard hyperbola has 1, 1. If I've changed my value to 1, 2, it must mean that my graph is stretched that way by a factor of 2. Please don't ever go, you've just added 1. Yes, I may have done. I may have actually moved the whole graph up by 1, but the fact that this is now also minus 1, minus 2 would suggest it's been a dilation. Now, as I've said before, when you dilate, you've got to remember that actually the asymptotes don't change because you're stretching away from the base graph. The helpful points in this situation became 1, a, 1, minus a. And what I'm trying to say there is you just take the y value and multiply by the scale factor. And the domain range, has it changed? Absolutely not, because I've not moved my graph up or down and I've not moved my graph left or right. Once again, here are the shortcuts. Here are the shortcuts. So if I'm going to dilate away from the y-axis, I would replace x with x on a. When you're going to dilate away from the x-axis, you replace y with y on a, where a is the factor of enlargement. And again, we do a lot more of that later on. Dilation from the y-axis, factor a. So this time we are dilating this way. My graph should have y equals 3 over x written on it. I should have labeled my asymptotes x equals 0 and y equals 0. There are no crossing points on my axes, so that's fine. So let's have a look. Domain and range, probably the easiest one to do first. Why? Well, because I've not moved my graph vertically or horizontally, so my domain and range stay the same. Likewise with my asymptotes from my standard graph. Helpful points in this situation, right? If I'm dilating away from my y-axis factor a, then what I notice is that I'm multiplying my x values. So in this situation, what was 1, 1, so where were we? We were there, has now moved that way to 3, 1. Important information, yes, in these transformations here. When you're doing this in a methods exam, it's always a good idea to actually use this algebra stuff to substitute in. I'll do more of that some other time in a different video. Then later, translations of rectangular hyperbolas. Thank you very much. We are translating now. So again, parallel to the x-axis, positive number of units in this situation. So what graph have I got here? Well, I've got the graph of y equals 1 over x minus 2, which suggests I'm moving it 2 units that way. So before I go any further, I know that my original graph had an asymptote at x equals 0. If I'm moving it 2 units that way, then I know that my asymptote now becomes x equals 2. And there's my line. So I'm going to write x equals 2 there, as I'm supposed to have done. I'm going to write y equals 1 over x minus 2 there to label my function. And I'm going to write that y equals 0 is my asymptote there, because I'm not actually moving it vertically. Helpful points, once again, showing the examiner that by moving the whole graph that way 2 places, I notice that my helpful point becomes 3, 1. This helpful point becomes 1, minus 1. Right? And that's how, in that situation, because both those points have moved, I know that I've got a translation. Earlier, if you remember, while this point here changed to 3, 1, this one stayed to minus 3, minus 1, which suggested we had a dilation. So all of these things, when you actually have questions that are application questions, you need to look at the graphs. Helpful points, tick, thank you very much. Domain and range, well, this time remember the range, because we're not moving it vertically, stays the same. So the only value that can't go in is 0. But my domain, I've moved my whole graph that way 2 places, which now means when I put 2 into my equation, I will get a value I can't have. Now, actually, as an aside, y equals... Sorry, that doesn't say y equals at all. Let's try it again. Y equals 1 over x minus 2. If ever you want to try and work out when asymptotes are for hyperbolas, or in fact for trunci, which we come to the next lesson, my advice is you just put that equal to 0. All right? Remember, you're trying to find out what value doesn't work, and the value that doesn't work is 0. So if I put x minus 2 equals 0, then I get x equals 2. That is my asymptote, because it's saying that if I put 2 into that equation, I end up with 0 out. So I can't have 2. Same things work if you remember with the square root sign. If I had x minus 2 under my square root sign, what do we know? We know that this value here can't be negative. So what I tend to do is test for when that's equal to 0. So again, in that situation, I'd put x minus 2 equals 0, so x equals 2. So what I would now know is the lowest value of my function there, my lowest value of a square root function, would have to be, and that's my standard square root function, in this situation, the lowest value would be 2. That would help me with my implied domain. Translations parallel to the y-axis, same as we've done before. This time we are now moving my whole function up. That would suggest that because I'm not moving it horizontally, that my x-axis asymptote stays at x equals 0. My y-axis asymptote now becomes y equals 2. Yep, and that is x equals 0. Label my function as, where can we put that? I don't have a lot of room. Y equals 1 over x plus 2. And what do we now notice? We now notice this actually crosses through my x-axis. And so in that situation, you would be expected to write down that solution. Now, how do we do that? Oh, that's really hard. I don't know how to do it. Yes, you do. Remember, when it crosses the x-axis, we know that y equals 0. So knowing my equation says y equals 1 over x plus 2, y equals 0 becomes 1 over x plus 2. Move the 2 over, minus 2 equals 1 over x. And so x becomes equal to minus a half. And lo and behold, there we go. Is that my crossing point? No, it is not. And so my advice to you is write on your graph that you would want minus a half, comma 0. That is your x-axis intercept, and it's the only one that there's going to be. All right? Helpful points. Once again, slightly run out of room on my graph. Let's actually make that so that you can see it. 1, comma 3. All right? We didn't move it horizontally, so there's no horizontal movement. But by moving the whole graph up by 2, my 1, comma 1 became 1, comma 3 because I added 2 onto each of my y values. Lastly, let's combine some transformations. Yeah. Here is my equation. Y equals 3 over x minus 1 plus 2. So when I look at this, I'm automatically thinking to myself that that value there is going to be a dilation factor 3 from the x-axis. I know that this value here is going to move my graph 1 unit positive because it's negative, and that one there is going to move it 2 units up. Whoop, whoop. Thank you very much. Now, while here, this one here is my final function, I would never in a million years suggest you do that, right? You have space for working out, and I always recommend sketches. So here is my original sketch. That is my graph of y equals 1 over x. Here is my y value, and here is my x value. Now, because this is working out, you don't really need to put any of this on. All I need to know is that my original points are 1, comma 1, and minus 1, comma minus 1. Right, so I've got to remember, they haven't given me the order in which to do it, so I have to do Dr. T. So dilations first. 3. So it's a dilation of 3, so I'm going to draw another quick sketch. Don't care what it looks like particularly, as my final sketch, as this sort of working out. So what do? I've moved it factor so that my y values have to be multiplied by 3. So 1, comma 1 goes to 1, comma 3. And what did I have? Minus 1, comma minus 1 goes to minus 1, comma minus 3. So I've now done the 3. Put a tick. I'm now going to do my reflections. There aren't any reflections, so done. So now my translations, and it doesn't matter which way you do it first, so I always do horizontally first. Quick sketch. Now I'm going to draw my asymptote because I'm going to move it 1 unit, so I automatically know my asymptote is x equals 1. Quick sketch, because again, it's not moving up. I know that I've now got to add 1 to each of my x values. I was at 1, comma 3. I now go to 2, comma 3, and I know that this value here is actually going to sit on the x-axis at 0, comma minus 3. Make sure that's a minus sign, Darren. All right, so that is my minus 1 done, and now what do I need to do? Now I move it up by 2. And again, another quick sketch. I know this seems like it's time consuming, but actually it really is going to save you time. Y equals 2, you've still got your asymptote at x equals 1. Another quick sketch, because I know it does that. Wow, what now happens here? So I've added 2 onto my y values. So this point here now becomes 2, comma 5. And this point here should become 0, comma, and what am I doing? Adding 2 on, minus 1. Now, as you can see from my sketch, that's horrible. All right, that doesn't actually look anything like it should do, but it's sort of close enough. So let's just check, is that what we ended up with? Yes, 2, comma 5 and 0, comma minus 1. 0, comma minus 1. Thank you so very much. Yeah? These questions will carry a number of marks, and I don't know that I am capable of being able to draw this straight away in my head. Yes, I could probably, if it was me, with my experience, go, well, I've got my asymptote there at y equals 2, I've got my asymptote there at x equals 1, and I could draw a rough sketch. Maybe I could do these coordinates in my head, but I imagine as it gets harder and harder and harder, I might make mistakes. Last part for this lesson, remember, when you are trying to solve for intercepts, you are trying to find out where they cross the x-axis and the y-axis. When it crosses the y-axis, you are putting x equals 0. So in this situation, I'd have y was equal to 3 over 0 minus 1 plus 2, which would be minus 3 plus 2, which would be minus 1. And as such, we would now say that 0 minus 1 was one of my intercepts, which we already proved, and put y equals 0, what we would have. We'd have 0 is equal to 3 on x minus 1 plus 2. Move the plus 2 to the other side to become minus 2 is 3 on x minus 1. Do a bit of funky algebra, and what do I get? X minus 1 is equal to 3 on minus 2, or minus 3 on 2. Add 1 to both sides, gives me minus 3 on 2 plus 1, which gives me minus a half. And so, fingers crossed, we should have minus a half, comma 0 as my intercept. And looking at my graph, do I have minus a half, comma 0? I certainly do. And so, I would label that point as well. In an exam, if you drew that graph as perfectly as that, then as far as I'm concerned, you'd have all of the marks. But you will be expected for all graphs to make sure that for everything that you do, asymptotes, domains and ranges, label your axes. And again, here that should have been x, that should have been y, or f of x, or whatever. And that suggests that we're at the end of this rather long video. Okay, thanks very much for watching. I look forward to seeing you for Trunk Eye. Thanks so much for joining us for that video. It was really good having you. Now, if you'd like to know when the next video is coming, why not click on subscribe? Alternatively, head on over to MaffsGuru.com where you can watch all of the videos on its own dedicated website. While otherwise, watch the video that's just popped up. It'll be part of this series. All right, take care. See you again soon.